the deploy file. This is how it looks like. It generates everything needed in order to do the injection. So let's run it again. I'm running the same executable, but now the code that was injected into the runtime says if the name of the application equals sensitive application.exe, open a reverse shell to the other side, right? So if everything works as expected, when I will execute this one, we'll see that the reverse shell will be opened on the right side. And let's see if everything is okay. And yeah, I have a reverse shell, right? So let's see that it is okay. Let's do an ipconfig. And I see that I'm over at the other side. Who am I? Well, I'm an administrator. Great, everything works as expected. Of course, I can close this one. And well, the reverse shell will still be open, right? So this is an example of a reverse shell which is injected into the runtime itself. So there are a couple of bad news, right? The bad news is that we have another attack vector to worry about. The runtime itself can be modified, and the problem is that there is very poor awareness regarding this issue. Very few people check the runtime. People trust the runtime too much. And we're talking about that code reviews, they do not check the runtimes. Code reviews, and I know because I do lots of code reviews, and most of the code reviews are being performed only at the application level, but no one checks the runtime itself. And of course, and again, forensics, they also do not check runtimes. So the bad code can be hidden over there. And the interesting thing about this this code is that, well, an MCR is cross-platform by definition. This is not like a payload that the malware developer has to write for Windows 32, 64, to Linux and to mobiles. He writes it once, and the virtual machine performs the conversion for him. So the same class can be deployed many times, right? Another interesting thing about this is that it is not relevant. It is relevant now for applications, but as time goes by, operating systems are started to be built on managed code environments. And if we look at the example from Microsoft, Microsoft has the Singularity project and the Midori OS that will be out sometimes, which is an operating system implemented solely with managed code runtime virtual machines. And the interesting thing is that an MCR inside the managed code OS is equivalent to a kernel level rootkit of today's operating system. Okay? Another bad thing is that MCR allows the attacker to do object-oriented malware. This is the name that I gave it to describe something that takes advantage of object-oriented, of inheritance, of polymorphism, of interfaces, and all the other stuff. And another bad thing is that, well, the runtime, since the runtime provides services to the applications, it provides a single control point for all of the application. And it also has a large attack surface, since many of the virtual machines are pre-installed on operating systems today. Think about Microsoft that provides the .NET CLR on almost all of the machines. All of the new machines, all of the new operating system today has the .NET CLR pre-installed. The good news is that, well, an MCR, since it is not a kernel level rootkit, it's an application level rootkit, it leaves traces, right? Since it leaves traces, we have the traditional countermeasure to do, so we can do about it. But we can also use some new techniques. For example, if you want to prevent, by the way, we cannot actually prevent it or maybe detect it completely, because think about it, what happens if OS level rootkit hides the presence of managed code rootkit? This is what I call the second level rootkit, right? But still, you can at least prevent it, maybe if it was before that. So, first thing that you can do is do code transformation. Basically, it will not prevent it completely, but it will make the life of the attacker harder. Think about it, what happens if, for example, we're talking about the second one, randomized libraries, which is something which is equivalent to ASLR. What happens if for every runtime it will contain a different code? So the same DLL, for example, that I created using ReFrameworker will be relevant only to one specific platform. Of course, the attacker can engineer a specific class for the specific machine, but it will be harder, pretty much harder for him. And we have the detection techniques such as the Windows file protection, some kind of watchdog such as tripwire, TPM for checking signatures, and of course the response for these kinds of problem, if we detect it, is to reinstall the runtime itself. Well, the good news is that we can use this kind of technique to do something good. Well, one of the good things is that you can do with this is to create your own runtime and to harden the runtime. We're using the same methodologies that antivirus is using. Well, antiviruses, they're using rootkit-like technique to protect against rootkit, right? We can do something pretty much close to that. We can deploy protection code inside the runtime. Of course, if someone changes the runtime, we can remove it, right? But until it happens, we have protection for the application. And of course, ReFrameworker can be the tool that implements this kind of thing. So we can actually, so we can actually restrict some kind of dangerous operations. You know, developers will always do mistakes, right? And even though we tell them millions of times, do not use dynamic commands, right? In order to prevent SQL injection. Do use HTML encoding. They will always make a mistake. But what happens, for example, if we remove the ability to do a dynamic SQL query from the beginning? So we can actually harden runtimes. By that, we change their behavior. So, for example, we'll disable the ability to do a dynamic SQL injection. We'll do an automatic HTML encoding for some inputs that we know for sure that we can do. And the next one is interesting. We can make, for example, a .NET application look like a Java application. What happens if I'm going, for example, to the cookie and change it to look like a JSession cookie? I'm confusing, I'm doing the same like against banner grabbing for web platforms. I can confuse the other side. So I'm confusing information gathering steps, and there are lots of other examples. So that the idea is that if I'm hardening the runtime, I'm actually having a better runtime if I'm comparing it to the generic runtime that the vendor provided me. Because it's generic and it's supposed to support all kinds of applications. Well, we are just about in time. So what I'm going to do now is going to do a summary, but we have a couple of minutes, so later on we can ask questions. So we've seen now at this presentation, we've seen that the malware itself can be hidden inside the runtime as an alternate malware playground. So that this is not kernel-level rootkits and device-level rootkits and BIOS-level rootkits. We're also having now application-level rootkits, virtual machine-level rootkits. This is something you should be aware of. Each runtime has its own steps, its own technique, the concept stays the same. The concept stayed the same, and the basic idea is that you need to know and need to investigate how to change a specific runtime, so that today I exposed the method of changing 3 runtimes, but well, the concept stayed the same, so we can extend it to other kinds of platforms. Another thing is that code reviews, forensics, basically everything that relates to security, you should start looking for runtimes. Do not take the runtime for granted. People can mess with the runtime. Developers that know that their code might be audited. Think about a rogue developer that wants to hide some piece of code that says, if the account number equals mine, give me more money that I should, right? Developer backdoors. Well, the developer knows that his code might be audited. So he will not hide the backdoor inside the application level code. It will hide it inside the runtime code, right? ReFrameworker that we saw allows us to do some kinds of runtime manipulations. Well, with ReFrameworker, besides of doing MCR like